This is Progress Podcast number 60, and today we're looking at part 2 of this Vortex Generator podcast series. And in podcast number 59, we looked at this paper that I have on screen now, computational modeling of 3 different sub-boundary layer vortex generators on a flat plate. And this paper looked at 3 different types. They looked at a rectangular plate, a triangular plate, so like a right angle triangle, and then a NACA 0012 airfoil placed perpendicular to the surface. So it has a wing tip, and each one of these devices creates a vortex. And if you haven't listened to podcast number 59 yet, go back and listen to that because we're picking up from where we left off. We left off from how these vortices wander around after they've been produced. And today we're going to be carrying on and looking at the vortex decay. So with any vortex that's produced anywhere, as it moves away from whatever it is producing it will start to decay because it's like there are a whole bunch of different reasons, but depending on what the vortex is, it can go through stretching and annihilation with other vortices and so on. So looking at how these vortices decay as they go downstream. So they say once the vortex is in the zone of interest, it's important to quantify its rotation through the vorticity magnitude for all analyzed planes. So they looked at, we covered in podcast 59, they looked at some planes going through cross sections to see what this vorticity was. And they have in figure 11, which we have here, the normalized peak vorticity in the streamwise directions. As expected, the decay tendency seems to follow an exponential law. So when you first produce these vortices from these vortex generators, they're at their strongest right then. And as you move downstream, they get weaker and weaker as you expect, and it follows an exponential. So like a 1 on X kind of curve. You can, if you can imagine that, or a ln curve kind of thing. So the rectangular vortex generator is the one with a higher value in the peak vorticity. The symmetrical NACA 0012 is at the same level as the triangular vortex generator for locations after 25 vortex generator heights downstream. Before that, the triangular vortex generator actually produces a vortex with a similar maximum vorticity as the rectangular vortex generator. So the triangular vortex generator, the vortices coming off of that, start off much stronger and then they decay much quicker than the other two. So that's interesting to note. Now they move on and they talk about the vortex size, and this is interesting because vortices also do grow in size as they go downstream. So they lose vorticity, they lose their strength, but they grow. And they say in some studies, such as Velter and Fernandez-Gamiz and others, the vortex size has been analyzed with a radial distance defined from the vortex center to the point where the azimuthal velocity reaches its maximum value. So in other words, they're trying to figure out how to quantify the size of a vortex. When do you say that a vortex is no longer present when you go further away? So they're saying that some researchers, they looked at the center of the vortex to the point where the velocity of in this region is now the same as a free stream velocity. Other people they say, on the contrary, in other studies, the size is measured from the vortex center to the point to which the streamwise vorticity decays to 0. And this is a much better way of doing it, in my opinion, because a vortex is really going to be producing vorticity. So if you don't have vorticity, then you're not going to really have a vortex. A better way is to look at the circulation. When you start seeing where the circulation, where the vorticity is 0, and then you can map the circulation around that, and that is also a very strong way of determining when a vortex ends. Another way, there are other ways actually. You can use the lambda 2 method. You can also use the Q criterion. These are 2 other methods. I'm not going to go into them. They're just mathematical equations which can determine when a vortex is present or not and where it really exists. So there's other ways. But for this second way, where you look at the center of the vortex and then you map it out to the point where the vorticity is now 0, and you say that this is the size of the vortex, they say for this second method, the streamwise vorticity distribution supposes a Gaussian one at the points contained in a normal plane to the flow. So in English, what this means is they say that it assumes that the vortex is uniformly distributed around the center, that it's not non-uniform at all. But they say, however, this statement is inconsistent at all points of the plane due to interaction of the vortex with the surroundings, as in the case of a flat plate. So what they're saying here is, when you have a vortex next to a surface, it's going to not be it's not going to be actually symmetric anymore. It's going to start changing shape and warping a little bit. Now, one reason why this is if you know potential flow. I'm not going to go into potential flow, but the general, in a nutshell, what potential flow says is if you have any flow feature next to a wall, the wall, such as a vortex, the wall acts as effectively a mirror. So what this means is if you have a vortex next to the wall, let's say it's 1 meter away from the wall, you theoretically have another vortex, which is 1 meter away from the wall on the other side in the exact same alignment as the vortex you do have in reality. And this vortex on the other side will be affecting the vortex in reality as well through inducing the flows and the velocities and also potentially breaking down the vortex. So that's what potential flow says, and that's why putting a vortex next to a flat plate makes it axisymmetric over time. It may start off symmetric, but it starts to break down axisymmetrically. And also vortices break down axisymmetrically often, usually anyway. So they say, therefore, they want to now find a more accurate way of determining the size of the vortex, because having a vortex next to a flat plate, it can be difficult to determine the size. So they say a more accurate parameter, such as the half-life radius developed by Bray, is designed to determine the vortex size. This parameter is defined as the distance from the vortex center to the spanwise points where the streamwise vorticity is half the peak vorticity, since the Gaussian distribution is undisturbed by the surroundings from this level of vorticity to the peak. Now, this is a very slapdash approach. It's not very accurate. I mean, you can say you can approach this with this way, but it's not that accurate. It's just a general idea, because you're now missing out a lot of the vortex. Even though the vortex does break down exponentially, you still do have a bunch with distance. You still have this parameter, the half-life radius, is an approach to the primary vortex size and only includes the primary vortex characterization. One cool thing that happens is when you put a vortex next to a wall, you often get a secondary vortex being induced out of the wall, because this primary vortex is now pulling fluid away, and that creates a vortex. I've seen, I don't know if I've seen a fourth vortex, but I've definitely seen at least 3 vortices being next to a wall, 2 of them being induced. This method, they say, for the computations carried out in this research, this method turned out to be not so accurate. After plotting the vorticity of the points in which the distribution, so a normal distribution, for the vorticity at the half of the peak vorticity height was not obtained. So in other words, even when you look at when the vorticity is half the maximum, it's still not going to be, and it's stretched to the point where now it's no longer axisymmetric. So this method does not work. So the spanwise distance from the vortex center to the points where the vorticity is half the maximum are not equal. So the symmetry was not found in the vortex distribution. So as a result, they say that they came up with a new innovative method to determine the size of the vortex. They say the vorticity distribution from the points were extracted to obtain the vorticity distribution normal to the one used in the half-life radius method. So in other words, they're just trying to find these points that have certain vorticity. Then they say 4 points have been determined where the vorticity equaled the maximum vorticity divided by 2, so half the maximum. 2 points in the vortex distribution was used to give you the major axis, and 2 were given to find the minor axis. So in other words, they want to now use an elliptical fit to map this vortex. They're saying, okay, the vortex is going to be approximately elliptical. So let's use a major axis and a minor axis to describe it. And that's what they do. Now, is this a good method? Yeah, it's okay. Assuming that a vortex is elliptical, you have to be sure that it is elliptical. A better way, I think, is by simply determining the area of the vortex that it takes up based on the vorticity equaling 0. That's the boundary. And then you find that area, and then you find the corresponding radius to a circle that would give you that area. And you say that's the average radius. Alternatively, you can always just find what the average radius is through a much simpler method, where you find the center of the vortex given the maximum vorticity. Then you find a line where the vorticity is 0, and then you find all the distances to that line around in a 360-degree rotation, and then you find the average radius. Those are 2 other ways. This method that they use here, where they use the maximum vorticity divided by 2 as the boundary, I'm not that fond of. I think it's inaccurate, but they went ahead with this. So from here, they then plotted the size of these vortices for these different vortex generators with distance downstream. So they say the rectangular vortex generator presents the larger vortex in contrast with the triangular vortex generator, and the symmetrical vortex generator, NACA 0012. However, the NACA 0012 vortex generator produces a vortex core near the wall with a larger size than the triangular vortex generator in some locations. Thus, a larger energy transfer may occur. So let's cover this quickly. In podcast number 59, which is the first half of this podcast series, I covered how the vortices move with respect to the wall downstream. So they start off at a certain distance away from the wall, and then how they move. So the vortices coming off of the rectangular vortex generator moved much further upstream, much further away from the wall. Let me quickly go back to this. Than the other two as you go downstream. So what that means is that the wall effects are going to be affecting these two vortices coming from the triangular vortex generator and the NACA 0012 vortex generator much more than the rectangular vortex generator. So this really agrees as well, where the as you go downstream, the vortex is significantly greater in area than the other two. The other two are very close in area and they're always much smaller. Now we get to a point which I'm not a big fan of how they've done this. So they're looking at vortex strength. And the way that you often determine what the strength of the vortex is you calculate the circulation. And you calculate the circulation around a closed loop of your structure where the vorticity is 0 or whatever constant you can manage. Usually you want it to be 0 because that means you get the entire vortex. So what they say here is the capacity of spinning that the vortex requires is evaluated through the circulation according to this equation, which is the line integral of a vorticity. However, or here they have a surface integral or whatever. It's the same sort of idea. However, in the present study, an alternative has been followed for the circulation. All points of the ellipse fitted in each plane has been calculated with the vorticity equal to maximum vorticity on 2. So in other words, they're using the maximum vorticity on 2 as the bounding line. So again, they're missing out a bunch of the vortex from this circulation calculation. So even though most of the vorticity is really contained within this region, there is still a lot of vorticity that isn't, and there's a lot of the vortex that is not. So the circulation calculations to get the strength of the vortex are not going to be accurate because you're missing out a bunch of the vortex. And even though you may assume that the vortex is well behaved in that this line that you have, most of the vorticity occurs in here, it may not. It really depends on the situation, and you may be surprised sometimes. So they've gone down this path. I don't like it. They should have made the vorticity 0 and done a bound integral around that, but they haven't. They went with the maximum vorticity on 2. And have plotted this. I'm not going to go into the details too much because I don't think it's accurate. I'm just going to give you the general trends. And what they've found is that the vortex coming from the rectangular vortex generator is always much stronger than this triangular vortex generator and the NACA 0012 vortex generator as you go downstream. And that kind of makes sense. We've found that it is bigger. It typically has a much a higher maximum vorticity. So that does make sense. But the value that it is greater than the other two in terms of the circulation, I don't think that's accurate. If you want to find it, you can find the paper in the link in the description. It's open access, so you can access it easily and you can look at it yourself. But I don't think it's accurate, so I'm not going to go into the actual details here. Just know that the vortex is going to be stronger for the rectangular vortex generator than the other two, and that makes sense based on the other values that they've found, which are more accurately calculated than what they've done this circulation with. So moving on to the wall shear stress, this is an interesting parameter. So with a vortex generator, I covered in podcast number 59 that you want to impart as much high momentum fluid into the boundary layer near the surface as you can. What this does is it increases the velocity in this region and it allows the boundary layer to stay attached longer. But if you're increasing the velocity in this region, it means that the wall shear stress is going to increase because the velocity near the wall is greater. And so seeing what the wall shear stress is for each of these vortices is really cool. So they've calculated this here. They said the wall shear stress is the result of friction within the fluid and between the fluid and the walls and is related to the fluid viscosity. The magnitude of the wall shear stress is dependent on how fast the velocity increases when moving away from the wall. The streamwise wall shear stress is determined by the equation 9. So it's equal to the viscosity, times by the derivative with respect to the distance away from the wall with the u velocity. So it's quite simple. It's just how quickly the velocity is increasing away from the wall times by the viscosity. So they say since the boundary layer stall is an adverse pressure gradient, since the boundary layer stall in an adverse pressure gradient is produced by a decrease in the skin friction, the wall shear stress increment quantifies the capacity of the flow to be attached due to its friction. This is a very interesting way of thinking about it. I haven't really thought about it this way before. What they're saying is, if you know the friction in the wall, you can also get a good idea as to how well the boundary layer can resist an adverse pressure gradient. So how well it will resist stall. And that's true, because if you have a greater friction, it typically means that you have a greater velocity near the wall. And it's changing much more rapidly. And that's usually quite good to resist stall and adverse pressure gradients. So that's a really novel way of thinking about it. So in figure 16, they show the value of the wall shear stress for each of these geometries. Let's have a quick look here. Have a quick looky-loo. Okay, so without any vortex generators, the wall shear stress is quite low. It's at 0.13 pascals perhaps. As soon as you put the vortex generators on this flat plate and they create vortices, the wall shear stress jumps a lot, like it's about 7 to 9 times the amount. And they say that at plane positions close to the trailing edge of the vane, the rectangular vortex generator seems to begin with a maximum value of wall shear stress in the near wake in comparison to the other geometry, so it's producing the most friction. And that kind of makes sense considering that we had the greatest the greatest vorticity there, and so it's going to be inducing a lot more flow. However, the NACA 0012 vortex generator has a comparable value for streamwise locations up to 15 vortex generator heights downstream. So it is quite similar. In fact, they overlap quite a lot, all the way actually to 50 vortex generator heights downstream as well. Both vortex generators produce vortices which are quite similar in terms of the wall shear stress that they induce. But for the entire time, for the entire distance, the vortex coming off of the triangular vortex generator is always about 10 to 20% lower. So that's quite interesting that even though the NACA 0012 vortex generator was producing vortices with a similar maximum vorticity as the rectangular one, as the triangular one, the wall shear stress is lower for the triangular vortex generator. What does this mean? First of all, it means that the friction drag for the NACA 0012 and the rectangular vortex generator is going to be greater, but they're also going to be more effective in delaying stall. At least that's how the theory goes. Whereas the vortices coming off the triangular vortex generators are not going to be as effective at delaying stall as the other two. So that's an interesting conclusion to end on. That's where this podcast will end. And so make sure to like, subscribe, and check out the Atmosphere Hawks instrument we make here to make your experiments better. And the way that does that is through measuring the density of air. So I don't know if you noticed, but we're aerodynamicists, and in the word aerodynamicist, there's the part aero, and that means air. So we should really be measuring the density of air in our experiments. If you don't, it can change by about 2 to 4% on a regular day. Like literally any day, it will change by 2 to 4%. And you're getting that air into your experiments because not only does the velocity of your wind tunnel depend on the density, so does the Reynolds number, so does everything. Like the condition of the air really affects this. So that means that your experiments are going to have this error in there. It's going to hide trends and you don't even know it. And it also makes validating CFD much harder. The Atmosphere Hawk gets rid of all those problems for you, and you would be surprised at how much easier doing experiments are once you have it. Like it makes it like child's play. So it's in the link in the description. Get one for your lab, and we'll see you next podcast. Peace out, amigos.